All right, let's get started. Kernel 2 is due this Thursday, so 3 days left. And again, if you have code from previous semester, don't copy from it. Best to get rid of it. And again, reminder that the grading guidelines is the only way we will grade. Make sure you go through it. And after submission, make sure you verify your kernel submission. One thing I just want to mention again, for kernel 2, VFS test may not test everything you need to implement. And again, I think some people lose points in kernel 1 because, they still don't understand what it means that every code path has to be tested. You have to provide, DBG statements to show that, those things have been tested. Okay, so in any kind of a function, if you have, if then else, right, if, something, right, okay, else something, okay, if you have something like this, there is a, a code path will go through this code, and there is another code path that will go through this code. So in both cases, you have to add a DBG statement, right? So you have to have a DBG, using the right format in here, and another DBG using the right format over here. Okay, otherwise you're going to lose points. Okay, so, you're doing the kernel code is, you shouldn't write a bunch of garbage code in your kernel. So you got to make sure that the kernel that you write, we want to see that, that you have test those code. Okay, so therefore we make this requirement so that every code path, you have to say that, you have to declare that you have tested somehow. Okay, so this is the way you declare it. You say if you run, if you run a certain kind of test, then, this will be tested. If you run, a certain other kind of test, then this code will be, will be executed. Okay, if it just so happened that this, the same test will exercise both, well, you can put the same thing over here. Okay, but you have to declare that this path is tested by this test, and this path is tested by another test or the same test. You have to make that declaration. All right, so make sure you do that in every one of your function. And if you write a lot of garbage, you have no idea what the code is doing, throw it out. If you can't test it, throw it out of your kernel. Okay, so that sort of brings up back to the point that what I posted in the class Google group again, is that, if there's no way for you to test some code, then you should just replace that code with a k-assert and just say that that condition can never happen, right? If you can never test that code, that's the same thing saying that that condition can never happen. Okay, so just get rid of it and, replace with a k-assert. And then what if that violate the code, violate the spec? Okay, because every function on the top, it said this is what you're supposed to implement, right? Okay, and yesterday I explained in the Google group post is that, the code, the documentation, these all come from the Brown University, right? They are used by many, different other universities. And I don't really want to change those code because when I get update from Brown University, I want to be able to just patch it up. Okay, so therefore I tend to keep those things there. Okay, the kernel spec, which is the web page, and also the grading guideline, that's for USC, that's for CS402. Okay, so therefore, since you're in that class, in this class, you have to implement based on the requirement, of this class. Okay, so over here I emphasize again, if you have the function spec that says you have to do this and that, but that will gain you 0 point, you don't have to do it. Just replace it by k-assert and say that that condition can never happen, in your code. All right, so don't spend too much time on these 0 point code. Okay, try to get it done and get ready for kernel 3. Okay. All right, so hopefully today we'll give you something about kernel 3 so you can start, looking into it. But I guess you need the, next lecture to cover the entire kernel 3. All right, so today we'll continue on the hardware side to talk about what a page table is. And also we're going to sort of go over some, different kinds of page table. Okay, so this is the basic page table, and I guess I didn't sort of mention this term. I'm gonna refer to this as the basic, page table. So it's 2-level, right? There's, if you take the virtual address, you divide it into two parts. The first one specifies the virtual page number, and the second one specifies an offset into that page. Okay, and the virtual page number get mapped into a physical page number, so therefore this offset work in the virtual address space also works in the physical address space. Okay, and the virtual page number will point to a page table entry, right? Because the virtual page number is the index into the page table, and this page table is the basic page table or the two-level page table. Okay, so they will give you an index, and what you get out of that index is a page table entry, and inside that page table entry, you have the physical page number. Okay, the physical page number is a page-aligned physical page address, right? So what you do is that you shift to the left 12 bits, and you get a physical page address, and then you add the offset to it that will give you the physical address for this corresponding virtual address. All right, in the page table entry, there are other stuff. We're going to see how these bits are used a little later, and we already know, things about validity, about, the protection, the read-write, and the other bits we haven't really talked too much about it. Okay, so when we get to the next set of slides, we're going to talk about, we're going to see that. All right, so for now, this is sort of the, sort of the top-level picture, right? And again, I mentioned the page table is too large, so we tend not to put the entire page table into the CPU or inside the MMU. Okay. So anyway, so this is sort of the basic scheme. Nobody really used the two-level or the basic page table, okay? But conceptually, that's what it is, okay? You take a virtual address, and then eventually that will give you a physical page number. You left shift 12 bits, you add the offset to it, and there you have it. And this page table, every process has a page table. The operating system is one giant process, even though the operating system, as we've seen in kernel 1, you can have many, many kernel processes, but they all share the same address space. Okay? Every user process, they have a separate page table. Each one is used to implement, their own address space. Okay? So therefore, in this picture, right, we have a blue process, we have a pink process, and we have the green operating system. Each one of them will have their own page table. Okay? And when you try to, reference a virtual address, you need to see whether that entry is valid or not. Okay, if it's not valid, you get a segmentation fault. You trap in, well, you get a page fault. You trap into the kernel, and the kernel might repair the page table. So in this example over here, the kernel will repair the page table entry, and then bring a page from disk, put it into the physical memory, and then have the page table to point to that physical memory, and then restart that memory reference. All right, so this is what we talked about last time. All right. So the page table is a little too big to fit into memory. So there are, different ways to fix this problem. In general, this is sort of a scaling problem, right? Something's too large, doesn't fit, So the general solution in computer science is that you do hierarchy or you use a hash table. Okay, so as it turns out, the same solution were used for page tables. Okay, so we're going to see some of these different kinds of page tables. The first one is to use two-level hierarchy, right? This is called page segmentation. Okay, so basically you use the first 4 bits in the virtual address as some sort of a segment register, tell you, which segment you're accessing. Okay, so this is basically go back to like the segmentation scheme, which is not very flexible, right? Over here, if you have 4 bits right here, you can only have 16 segments, right? So you have code, data, BSS, maybe the heap, maybe the stack. And then every memory map file, you need a separate segment, which means that you can only have, 11, something like that, memory map file. Okay, so this is really not very flexible. So this is really not used. Okay, we're going to see what Intel uses. This is what Intel does. Okay, so Intel uses this, also uses hierarchy. Okay, so this is the forward map page table, also called multi-level. Okay, because they take the virtual address and chop it into 3 parts, okay, one more than the basic level, the basic page table. So in this case, the 20 bits that was over here before get divided into 2 parts. Okay, the last part, Intel still used the 4 kilobyte pages, so in the end, the offset is still, 12 bits long. Okay, but the first 20 bits is divided into 2 parts. Each one is 10 bits long. The first part is actually called page directory entry. Okay, so this gives you a page directory number, and then the second one is the page number. Okay, so what happens is that you divide things into hierarchy. So the first one will address a page directory table, and this one, the number over here, give you an offset into that page table. Okay, so this is a higher level page table. Okay, so in this case, what happened is that if you take this, the beginning of this table, you add this number over here, and that will give you the page directory entry. So the page directory entry, it looks just like a page table entry. Okay, so what it will do is that it will point you to the next level page table. So in this case, this entry will be left shifted, 12 bits, okay, and that will give you the beginning part of this page table. All right, and this page table looks like the previous table, but in this case, only the middle 10 bits will be used to address, this page table. Okay, so therefore, how many entries are here? Well, you use 10 bits, so it's 2 to the 10. There's 1024 entries over here. All right, so this is much smaller. Instead of having, in the previous case, 1 million entries, over here we only have 1,000 entries. Okay, potentially you can have 1,000 of these page tables. So in the end, it's the same size as the previous one if you add up all the possible page tables. Okay, but individually, this one is kind of small. Okay, so this, you use the middle 10 bits to give you an offset into this page table, and then what's in it is, again, it's a page table entry. So this one just looked like the previous one. Okay, and that will give you a physical page. It will point to the beginning page address. You add the offset to it, and then you get, the actual, physical memory location correspond to this virtual address. All right, so instead of doing one translation, you do two translation. Okay, so that's the, and this is what Intel has. So what is the advantage over here? Okay, so in the previous case, right, when in the basic page table scheme, the size of the page table is 1 million entries, and every entry is 4 bytes long, right? We sort of calculate roughly it needs 4 bytes. Okay, so that's 4 megabytes. Okay, so this one, so if you look at this table, right, you need this table. This table is required. Okay, so the page table, the page directory table, you only need one of them. And how big is this table? Okay, the number of entries over here is, again, 2 to the 10, right? So there's 1024 entries over here. Okay, each one of them is 4 bytes long. Okay, so this whole thing is 4 kilobytes. Okay, so of course it's not a surprise that this fit into exactly one page. Okay, so one of these page table fits exactly into one physical page. Okay, so therefore the address over here, of course, you would like this page table to be also page aligned, so this entire page directory table will fit into one physical page. All right, so this is 4 kilobytes, right? And let's say that you have a small program. The small program only have, does your program need a stack? Of course it needs a stack, right? Does your program need code? Of course it needs a code, right? So in the end, if you look at all these entries, maybe the first entry, validity is equal to 1, and the last entry, validity equal to 1. Everything else, validity will be equal to 0. All right, so it is possible that you need, the stack, the text segment, you need data segment, you have a small, BSS region or small data segment, and you have a small stack. So therefore, in that case, the smallest, page table requirement for your user process is that you need one of this, and you need 2 of these things. Okay, and this 4 kilobytes, 4 kilobytes, 4 kilobytes, that's a total of 12 kilobytes. Right, so in this case, for you to run one user process, the smallest number of page table that you need is 3. Okay, as opposed to this one large table that's 4 megabytes long, now you reduce the requirement down to 12 kilobytes. All right, so this is a major advantage over the original scheme. Okay, so that's why sort of Intel, choose things this way. Okay, so again, the page table, you should think about it as sort of some kind of a, overhead in the kernel, in the kernel, in order to do the address translation. Okay, so therefore you want the overhead to be as small as possible. Okay, so therefore, of course in this case, again, you're trading off space with time. Right? Why is that? Right, because right now when you do translation, you have to go through two levels of page tables. Right? In the previous case, you do one translation to get to the physical address, and you use that physical address, set it to the bus, and then you can get get the data. Okay? But now you have to go through one level of translation. This one will give you a page number. You go to the physical memory, fetch that page table entry, and that will give you another address, and do another computation, and then go to the memory bus again in order for you to get to the actual memory location. Okay, so now instead of going to the bus once, you have to go to the bus twice. So you are twice as slow for every memory reference, okay, but you save a lot of space. Okay, is that a good trade-off? Not really, right? Because, if you're running your CPU twice as slow, that's a big penalty. Okay, so we're going to sort of address that problem of being too slow a little later. But keep in mind that over here you save space, but we're running twice as slow. Okay, and twice as slow is really too slow. Okay, all right, we're going to come back to that. Over here it says the minimum requirement is 3 pages, right? One for storing the page directory table, and the other 2 for storing the page table. Okay, so this page table entry, right? Some of the validity bit is going to be equal to 1, right? And then maybe some other side with ability equal to 0. Okay, but this page table, v is equal to 1, v is equal to 1, everything else a big 0 over here, and they all point to invalid physical pages. All right. Okay, so the main drawback is, how slow this is. And I mentioned that at the page table, the base of the page table needs to be a physical address, because if it's a virtual address, then you sort of have a self-reference, then you get an infinite loop. If the entry is not valid, then you can never resolve memory references. Okay, so the base of the page the page directory table, okay, this needs to be a physical address. And on the Intel processor, inside the CPU, there's a register called CR3, and CR3 stores the base address of the page directory table. Okay, so therefore, every time when you switch to another user process, you have to load CR3, with the correct address for the page directory table for that user process. Okay, when you switch to the kernel, of course, this thing also has to be changed. Okay, so as you trap into the kernel, you will see that, I guess in Unix code, if you look around, you will see that, the CR3 register is set so that the kernel can execute properly. Okay, and right before you return to user process, again, you have to restore the CR3 register so the user process can use the correct page table. All right? Okay, so the CR3 register contains physical address, and the page table entry over here also contains physical page number, right? And if you shift to 12 bits, you get a physical address, okay? And the physical address will give you the first address also of the second level, page tables, okay? So all these things contains physical addresses, all right? Okay, so that's that's basically Intel, okay? For Intel, the page table entry is actually well documented, okay? At the beginning of today's lecture, I showed you that picture of the validity bits, the write, the access, the protection or something like that. Again, that picture is kind of like a higher level concept. Doesn't really map directly into Intel. If you go into the kernel 3 FAQ, there's actually a link that will take you to the Intel processor spec. And if you look at the hardware spec, then you know exactly what this page table entry looks like. Okay, so this page table entry is understood by hardware, so it has to be of a certain bit pattern, because this thing gets loaded into the MMU, and the hardware is going to execute, is going to perform its operation based on the bits in here. Okay, so before that thing gets taken into the processor, it needs to be in the right format. All right, in kernel 3, you actually, I guess one of the first exercise we're going to do is to see how these, bit pattern gets set, inside the kernel when the kernel initializes. Because as we talked about before, right, the code that you are that you are debugging and you're running in all the kernel assignment, those are in virtual address mode already. Okay, so therefore the page table for the kernel is set up before the bootstrap code. All right, so therefore I'm going to sort of tell you where that code you have to read in order to understand how the kernel page table is set up. All right. Okay, so this way is not the only choice. There are other choices. One is called linear page table. So this one, looks like the page segmentation. Okay, in the beginning you have, instead of 4 bits, they have 2 bits, and over here they have 21 bits, and the page size is 512 bytes instead of 4 kilobytes. So this corresponding to an old architecture that's used by the Digital Equipment Corporation's VAX system. Okay, so this is really currently not in use. So it's kind of a sort of an interesting idea. Intel later on tried to revive it, but it really didn't work out. So what happens is that in this particular scheme, called the linear page table scheme, the first 2 bits give you the space of where you are. So it's kind of a sort of a, so it's not a segment register, but it's some sort of a space. Okay, so it give you, so 2 bits give you 4 choices, right? 0001, 1011. Okay, so it turns out you can sort of interpret it, the 00 and 01, they're kind of like user space page table. And then 10 and 11, actually 11 is not being used. So 10 is like a kernel level, page table. Okay? As it turns out, the real way to interpret that is that the 00 and the 01 space, what it will give you is that, the page, the page table entry inside over there will give you another virtual address. Okay? So instead of giving you a physical address, this particular scheme will give you a virtual address. Okay? So therefore, this entire page table, even though it's pretty large, it sits in, virtual space, okay, so in that sense, a lot of these entries, they, you don't have to supply them, okay, because they can all be, they don't really have to be present, so you can actually have a big hole inside, this middle of the page table. Okay, so this way, that only the top entries are valid and only the bottom entries are valid for a conventional program. Right, again, for a conventional program, at the low address space, you have the code segment, data segment. At the high address space, you have stack. Okay, so the way that you can make sure that, the middle part is not being used is that what happens is that for, for space 00 and 01, you say, well, how many entries are used over here? Okay, so it's kind of like the base and bound making a comeback over here, where the base in the beginning is over here, and then there's a bound to tell you how many entries are being used. And also at the top, you start with, the last location, and then you have a negative bounds that tell you how many entries are being used. Okay, so in that case, you will use only a few entries over here. All right, so even though in this picture, it looks like there's going to be 2 to the 21, which is 2 million entries. But in reality, it's much, much smaller. Okay? The textbook used this picture to sort of describe what kind of translation that needs to be done. But the basic idea is that after you do the first translation, you get a virtual address, which you have to do another translation. Okay? Actually, what I'm going to do, I'm going to put a little gray X over here so that you don't really have to, pay too much attention to this very confusing picture. Okay? This picture, I got it from the textbook. So you can try to understand it. To try to figure out exactly what it means, but you won't be responsible for the exam. Okay, and also the scheme is not being used these days, so we're going to pretty much skip that. All right, and over here, this picture sort of talk about in the linear page table, right? We basically use the length register to tell you how much. Actually, it's this slide. Okay, we use the length register to tell you how many of these linear page table entries are being used, so that in the middle you can have a big hole. Okay? So again, this work so one of the reasons this is not used these days is again because of memory map file. When you have memory map file, then the memory that you use is no longer contiguous at the high end, at the low end, because you're going to end up using memory all over the place in the middle. And also because of multi-threading, you're going to allocate stack for all your threads, and again they're going to take up space in the middle of the address space. Okay, so in the good old days, when you only have a single thread inside every process, this is probably not a bad way to go. And VAX was a very successful computer. Lots of people were using it until when we start having multi-threading. So therefore, the address space looks like the stack is everywhere, memory map file is everywhere. Then using these 2 length register is no longer enough to cover that big of a page table. Okay, so this spells failure for the linear page table. Okay, another alternative, right? So we see one approach to solve the page table too large problem is to use hierarchy, right? The other approach, of course, is hash table. Okay, so you can also use hash table. And hash table, we're going to start with the 2-level scheme, right? We're going to have 20 bits over here, 12 bits over here. And the virtual page number, instead of having, 1 million entries, okay, we're going to use a hash table. We're going to take this 12 bits, send it to a hash function. Okay, and a hash function, right, again, from data structure, a hash table, when you hash something, you're going to get a bucket number. Okay, and the bucket number tells you which bucket to go to. So in this case, the output is only 2 bits, so the output can only be 4 buckets. It can either be 0001 or 1011. Okay, and start with the bucket is a conflict resolution chain. Okay, so over here, this picture shows you that these are all the entries that all hash to the value 01. Okay, so there might be a lot of entries over here. You know, in this example, 3 of them is going to hash to 01. So whenever you try to look up the hash table entry, you will first have it go through the hash table, give you a 01 over here, and then what you do is you compare what's inside over here with what's actually stored there. Okay, so over here what you do is that you compare the tag. The tag tells you that this entry, what is the virtual page number. Okay, you compare the tag against the virtual page number. If they are equal, then that means that this page table entry inside of this entry, this is the one that you want. Okay? If the tag is not equal to the virtual page number, that means that you need to follow the linked list and go to the next location, okay, to try to find the entry that you're looking for. Okay? So in this case, what you will do is that you'll follow the next entry. The next entry is following the link pointer that will go to another memory location. Okay? And again, over here, there are 3 fields. You compare the tag against the virtual page number. If they're equal, then this is the page table entry that you're looking for. Otherwise, you follow the link and then compare this tag against the virtual page number. Okay, if they're equal, then this is the one you use. In this case, the last link go to the null pointer. Okay, so in this case, you traverse down the entire page table and you didn't find a match. All right, so in this case, it means that this particular entry does not exist. So therefore, this is a segmentation fault. All right. So when the operating system kernel decides to allocate a new, so for example, if you use a program called memory map, you want to create a new memory segment. Okay. So you're going to create a new place to put this data in. So what you need to do is that you need to take, let's say that the new memory segment has a virtual address like this. Okay. And again, you take the virtual page number, you feed it through the hash table, find out which entry that you have over here, and then you can create an entry like this, and you append that to the end. Okay, so for example, if this one also hashed to 01, what you will do is you create another entry over here, right? It's a linked list. We know what to do with linked list. The tag that we have over here is going to be exactly this virtual page number over here. Okay, the link is going to be null, and we're going to have this guy point to this guy. And the page table entry for this page table, we're going to put it right here. Okay, so this way, next time when you try to use this page table virtual page number, again, you will hash to this bucket, and you will search down, and eventually you're going to find the virtual page number right here. You're going to get a hit, and therefore you're going to use this page table entry. All right, so the operating system needs to maintain this data structure for the page table. All right, so even though this one looks very, very different from the very simple page table, but conceptually they are equivalent. Right? Instead of having a 1 million entry page table entry, now you have a hash table implementation of this 1 million entry. Okay, and the difference over here is that you're only going to have entries where you're only going to have a data structure if an entry is being used. Okay, if the entry is not being used, then they are not going to appear in this data structure. All right, so again over here, the reason for doing this is to save memory. Okay, and what do you pay when you want to save memory? You pay in terms of speed, right? Because what happens is that every time when you try to access the virtual address, you have to walk down the conflict resolution chain and doing all the comparison in hardware in order for you to find, to find the right data structure that have the match tag against your virtual page number, so you know which table entry to use. All right. So in this example, right, in the end, if you want to access, if this is the virtual address that you're looking for, in order for you to get to the page table entry, you're going to have 1 memory access, 2 memory access, 3 memory access, and 4 memory access. You have to go to the bus 4 times in order for you to get the page table entry. All right, so, is being 4 times as slow reasonable? Of course not. All right, so again, this, so I guess I'm sort of trying to get to the same point as the previous case. When you have the multi-level page table, the performance is, again, very, very poor. Okay, so the solution for this is to cache the page table entries. Okay, so these page table entries, Okay, what you need to do is you need to cache them. Where do you need to cache them? Well, you need to cache them inside the MMU. Okay, so therefore, when you try to look up a page table entry, you don't have to go to memory and look for it. First, you check inside the MMU, say, hey, do you have a cache copy of this page table entry? All right, so later on, we're going to see exactly what data structure is being used inside the hardware for caching a page table entry. All right, for now, you can just suffer through the performance problem of these implementation. All right, so over here, okay, so this works really well also for sparse, sparsely allocated page, address space. Okay, so the idea over here is that if this is your address space, okay, and if your address space is very sparse, for example, if you have a stack over here, you have a stack over here, you have a memory map file over here, memory map file over there, and then at the bottom you have the text segment, things like that. Okay, if your memory usage is spread out all over the virtual address space, okay, so that's kind of a sparse allocation of your address space. In that case, this works really well. Okay. But in reality, that's really not the case, right? If you have a simple program, and if you're not doing multi-threading, then basically, the bottom part is being used, the top part is being used, and the middle part is empty, right? That's sort of a typical program. Okay, you're going to get fancy, you got to get multiple threading, then it's becoming more sparse. But basically, the simple programs, they all look like this. Okay, so if you use this, then what happens is that at the beginning, when you start accessing these memory locations, you're going to end up going through multiple, you're going to have conflicts, okay, because in the bottom part of your address space, you're going to end up using, many, many pages, tens, hundreds of pages, and all that kind of, all those pages is going to end up with different data structure right here. So you're going to have a long linked list, and, your performance is going to suffer because you're going to end up traversing this linked list all the time. Okay, so one way to do this is to shorten the linked list, right? And that solution is called clustered page table. Okay, in the clustered page table, you start with one page address, but you put the next few pages all inside the same data structure. Okay, so this one, you take the page table, you hash it. This simple scheme, hash it into just 2 bits. 0 and 1. 0 is here, 1 is here. Okay. But the data structure that you use over here has many, many page table entries. This one has 1, 2, 3, 4, 5, 6, 7, 8. Okay? So starting with one base address, starting with the tag right here, the next 8 pages are all summarized over here. Okay? So if you have a match, with this address plus any of the next 7 addresses, then you can use one of the page table entry over here. So therefore, on the average, the length of the conflict resolution chain is going to be relatively small. Okay, so this, again, you trade off space with time, right? Because what happens is that if your segment, if your contiguous address space that you have allocated turns out that it's actually sparse, then you're going to end up with a lot of entries that are not being used, right? If you have something that if you have a memory map file that only uses one page, then that means that the other 7 entries, they will point to null. Okay, so therefore you're going to end up with wasting space, right? And in this case, we are we're choosing to waste space so that for most of the memory access, you traverse down a small number of hops in the conflict resolution chain. All right, so that's cluster page table. If you want to minimize the number of page table entries, okay, if you want to sort of cut it down to the bare bone, what should you do, right? I mean, so again, we're trying to sort of, minimize the overheads there. As it turns out, there's another way to actually minimize the page table entries, okay? And this is called the inverted page table. And so inside the inverted page table, so the idea over here is that you're going to have one page table, and it turns out that this one is shared by all the processes, in your system. Okay, so instead of having one page table per user process, we're going to have one giant page table that's shared by everybody. Okay, so in that case, here's my inverted page table. Okay, over here, this is the entries for user processes and different pages. Okay, so therefore, in order for me to tag every one of these entries, I actually have to say which user process they belong to. Okay, so over here, every entry in this data structure is going to contain the process ID, okay, for which process they belong to, and then the other stuff like page number and the physical page number. Okay, so this is going to be sort of the data structure, kind of like, the page frame data structure for me to store this information. Okay, so when I use this, so how do I use this? Okay, okay, so when you're running a particular user program, right, it generates a virtual address to reference a piece of virtual memory. So what you would do is that you would take the virtual page number, okay, you're going to add it together with the process ID and feed all these information into the hash table. Okay, so this hash table is going to be, it's going to also take the process ID, so it's different from the previous case. Okay, and this one is going to give you a global hash table. Okay, and you follow the global hash table entry, and that will give you one place into the inverted page table. All right, but that will only give you the beginning point because, you're going to have conflicts, right? You can have multiple processes, multiple page table. They all happen to hash to the same entry. Okay, so in this case, we're going to have a conflict resolution chain, and the conflict resolution chain is going to be built inside the inverted page table. Okay, so the inverted page table, this one not only has PID, has a physical page number, and, virtual page number. In addition, it also have the link field for the next guy on the conflict resolution chain. Okay, so in this case, when you get there, it will give you the beginning part of a page table entry. Okay, in this case, what you will do is you will compare the PID with the current process ID, compare the, sort of the virtual page number. This one is also, again, it's the tag, okay, with this virtual page number. Okay, if they are both equal, then you know that this page table entry has the right thing that you want, which means that it has the correct physical page number that you can use. Okay, if it's not equal, then you follow the link, go to the next guy, and again compare the PID, compare the tag, and if they're the same, use the the physical page number. Otherwise, go to the next guy, and you continue like that. Okay, if you do something like this, then you only need one inverted page table that can be used by all the user processes out there. All right, so this one has very small overhead, but again has the problem of performance, right? Because again, the hardware needs to be able to traverse all these entries in order to find something, and then generate many reference to physical memory before they eventually find the final place that it has to go to get that physical page data. All right, so all these things are very slow. We're going to see how the hardware actually speed all these things up, okay? And that, so we're going to use a cache inside the CPU, and that cache has a special name, and it's called a translation look-aside buffer. Okay, so of course the translation stands for address translation. Look-aside meaning that, you sort of look sideways, to find this thing that are cached. So before, so the picture that you see, right, is that when we see translation, we see some virtual address get translated into physical address. Okay, so over here it says, well, before you do the translation, you sort of look aside to look for the translation look-aside buffer to see if the data that you're looking for is already there. If it's already there, then you don't have to go through the address translation, right? This is the address translation. Okay, so you look to the side to see if it's there. If it's there, then you just fetch the the information. In this case, what is the information? Well, the information is the page table entry. Okay, so you're going to get the page table entry directly from the translation look-aside buffer instead of going through memory to find that entry. All right? So hopefully, and this translation look-aside buffer is inside the processor or inside the MMU, so therefore this lookup is going to be very fast. Okay? All right, so here is sort of another picture. Right? Here is the memory bus, okay, or the system bus, right? Depends on what actually is on it, bus. Okay, and inside the processor, you have the translation look-aside buffer. Okay, so before you do the address translation, you look into the translation look-aside buffer and to decide if things are there or not. If it is, then you fetch from the translation look-aside buffer instead of going to the memory bus. Okay, so the difference in speed is that there's about a 1 to 10 difference between what's inside the processor and what's going to the memory bus. Okay, if you go to the memory bus, it's going to be 10 times as slow as accessing this memory. Okay, so you're still accessing two memory access in order for you to get to the page table entry. Okay, except that the first one is going to be really fast if you get a hit. Okay, and then eventually that will give you a memory location for the physical memory, while the second time you have to go to physical memory. So in this case, the total cost is going to be 11 times the speed of the memory inside of the CPU, as opposed to 20 times if you go to if you use the Intel scheme and do the multi-level scheme, you're going to go to the physical memory twice. All right, so this one is going to be almost 50% speed increase. All right. Okay, and this scheme sort of works with everything. Okay, if you have a what do you call that? The hash table scheme, right? You have to walk down that chain. Okay, so again, don't walk down that chain. Right before you walk down that chain, first look into the translation look-aside buffer to see if you have that page table entry. Right? If you have it, then you don't have to walk that data structure because you jump directly into the page table entry and you can access memory. All right, so that will save you quite a bit, even if you have a hashed solution. All right, so what does the translation look-aside buffer look like? Okay, so so this is a typical hardware cache. So for all of you who have taken architecture or who are doubly major, you're probably familiar with this. The typical translation look-aside buffer uses a set associative cache. Okay, and the set associative cache works, like the following. It has multiple levels. Okay, so you will take the virtual address, right? We throw away the last 12 bits because the last 12 bits offset into a physical page, so we don't really need that. We're going to take the first part. We're going to divide into two parts. Okay, one is called the key. Okay, and that one tells us which cache line to use. So these are cache lines. Okay, if we have 64 cache lines, then we need 6 bits over here. Right? So over here again, if we have 6 bits, that means that we have 64 cache lines. So by looking at this key, it will tell us which cache line to use. Okay, when you go to a particular cache line, okay, there's going to be multiple buffer there. So this is almost like the cluster scheme when you have a conflict resolution chain, except that instead of having a conflict resolution chain, it's using a conflict resolution array. Okay, so this array over here is going to be of a certain size. Okay, in this case, if it's a two-way set associative cache, then the array we're going to have 2 entries. All right, so what you do is that you take the virtual page number, in this case, the first 14 bits of it, you compare that against what's stored inside the set associative cache. If they're equal, then the corresponding entry is the one that you use. Okay, so if you have a two-way set associative cache, what it means that, for this particular key, there's going to be 2 entries over here that you can compare them in parallel. Okay, so the difference between this and the clustered, hash table scheme is that for the hash table, this is considered a collision, and you use a linked list in order for you to search through the linked list to find the right page table entry. Okay, so every one of these guys is actually, let me go back a few slides. Okay, every one of those entries is like, okay, it's like this guy over here. All right, so over here, this entry, this particular hash value has 3, data structure that are linked in a linked list. But if you imagine that, what if I can put all these 3 things in parallel so that when I search through these 3 entries, I will search them in parallel. Okay, when you can search them through in parallel, then what you have is a set associative cache. Okay, so let's go back here. Okay, so for a two-way set associative cache, what you do is that you take this tag and you compare with all the tags over here in this particular entry and compare them in parallel, and one of them will have a match, or maybe none of them will have a match. If none of them if none of them has a match, then what you do, you have to go to memory to try to fetch this. Okay, so basically at that point, you skip the translation look-aside buffer and go through the normal translation and try to look for that page. Okay, so and actually these days on Intel, what Intel has is a 8-way set associative cache. Okay, so therefore, every one of this cache line will have 8 of these buffers. So whenever you try to generate a virtual address, the virtual page number, the first 14 bits, is going to compare against 8 of these entries in parallel. Okay, so this is very expensive in hardware because you need very fast hardware to do all these comparison, and then you need to be able to do this in parallel, and that turns out to be very costly in hardware. Okay, so usually this data, this hardware inside of the MMU tends to be small, because you have to do all these comparisons in parallel. All right? Okay, so what happens is that when you compare against all these things, and none of them has a hit, okay, none of the tag compared to this one, what you need to do is that you need to go through your normal way, going through the address translation in order to find that page table entry. So if you have a multiple level, you have to go through the page directory, you have to go to a page directory entry and then go through the page table, and that will eventually give you a page table entry. And when you start using that page table entry, you need to cache it inside of the MMU. Okay? So in that case, what you need to do is that you need to take these 2 entries, decide which one you want to throw away, right? Because now you're going to have a new tag. So what you do is that you're going to pick one of these 2, you throw away, and the one that you just used, that one goes into the tag, and the page table entry get cached in here. Okay, so in that case, the next memory reference, so the next memory reference that you're going to generate, well, hopefully it's going to be using the similar virtual address, right? Only the offset is different, and the beginning part is going to be identical. So therefore, the key will point to the same place as the entry that you just replaced. And now when you do a search for the tag, you're going to get a match because you just replaced this entry with the stuff that you just look up. Okay, so this way, you're going to get a page table entry, you're going to get a hit, so therefore you don't have to go to memory for that. All right, and then when you try to get to the data, try to fetch the data from memory, then you're going to use the page table entry to give you, to generate a memory reference on the memory bus to get the actual data. All right, so this one, if you get a very high hit rate in a translation look-aside buffer, right, every time when you compare the tag against many entries in the cache line, and if you get a hit, well, that's a translation look-aside buffer hit. Okay, if all of the comparison is returned false, you have to go to the real memory to get the data, then that's a translation look-aside buffer miss. Okay, so what should be a good hit ratio? Okay, so if you think about it, right, if I go to this entry, okay, if I go to a random memory address, okay, I'm starting to, the first time, I'm going to get a miss, okay, because chances are all these information will be wrong. I'm going to get a miss. I'm going to fetch a data from, I'm going to fetch a page table entry from the actual page table, okay, and put it into this memory location. Okay, from that point on, hopefully the next 4 kilobytes that I have to access, I will get hits. Right, because the next 4 kilobytes memory references, hopefully they will all have the same thing, right? If the first entry that I access is page line address, okay, and then if I access 1 byte at a time, then maybe the next 4,000 accesses, I will have translation look-aside buffer hits. Okay, if I access data 4 bytes at a time, then the next 1,999 or 1023 accesses, I will have hits. Okay, so I'm going to have 1 miss for every 1024 accesses. Okay, so my hit rate should be really, really high. Okay, so I should expect my translation look-aside buffer hit rate is going to be 99.9%. Okay, so therefore, even though when I try to save space by using, a cluster page table, I have to walk down that particular chain, I only have to do that once every 1,000 memory references. Okay, so by having a good translation look-aside buffer is going to pay off really, really well. Okay, and also the idea over here is that once I start running a user process, right, if you look at this translation look-aside buffer, I'm going to load in the translation look-aside buffer for this user process, okay, or I'm just going to clear the translation look-aside buffer. When this user process is starting to execute, I'm going to starting to load up the translation look-aside buffer with whatever things that I look up. Okay, so after the user process start running for a while, then pretty much that user process should always get hits. Okay, so unless you start accessing, doing recursive calls, starting using new stack space that I never used before, but most of the memory reference is going to have hits. All right, so therefore I do expect that after, my user process are running for a while, the hit rate should be about 100%. All right, and the performance of this is very crucial because then you don't have to go to real memory to look up a page table entry. Okay, and also this is the reason that when you run, so when you switch to a different user process, what do you have to do? All right, when you switch to a different user process, the user process has a completely different address space. Okay, if you use the virtual address for the new user process, is it possible you're going to get a hit? Right, you're going to get a hit, and that will point you to a physical page table entry, and that will be the physical page that belongs to the wrong user process. Okay, so therefore, when you switch to a different user process, you have to replace the translation look-aside buffer of the new user process. Okay, so that it's a little bit too much work to do every time when you switch from user process to another. So what normally done is that when you switch from one user process to another user process, you flush the entire translation look-aside buffer. Okay, you said that the entire content of the translation look-aside buffer become invalid. Okay, so therefore when you switch to a new user process, you really want to run that user process for a little bit. Okay, you don't want to sort of switch, switch user processes very often, because otherwise the new user process, what it will do is that it will have a lot of translation look-aside misses. Okay, once it completely load up translation look-aside buffer, if you switch to another user process right away, then all that work was wasted. Okay, so therefore it's actually quite important that when you switch to a new user process, you got to let it run for a while. Okay, what is a while? Okay, I mean a while might be, I don't know, 1 millisecond, 5 millisecond, 10 millisecond. You got to actually have it to run for quite a while in order to reap the benefits of all the work that you just spent loading up the translation look-aside buffer. Okay, you probably heard of, when we switch, every user process has some sort of a quanta that it has to execute before you switch to another user process. Right? So when you start a user process, you set a timer for its quantum or quantum. When it uses up its time quantum, and then you switch to a different user process. Okay, so the time quantum cannot be too small. If it's too small, it's going to impact the performance, the hit ratio of the translation look-aside buffer, and then you're going to end up with very, very slow user processes. Okay, so that's why the user quantum is actually reasonably large so that we can reap all the benefits of the translation look-aside buffer. All right, so, crucial in performance of the CPU. Okay, so there are other translation look-aside buffer, right? So this is, again, go back to your architecture class. There are different kinds of hardware caches. One is called fully associative cache. Okay, a fully associative cache, the number of bits in the key is 0. Okay, and then, so there's basically one line. Okay, and this one line will be able to do all the searches in parallel. Okay, so a fully associated cache, depending on how big your translation look-aside buffer is, you might have, I don't know, 1,000 entries over here. Okay, and you will be able to do all the comparison of 1,000 entries in parallel. All right, so clearly this is very, very expensive to do that kind of a parallel operation, inside hardware. Okay, so usually you don't see, fully associative, cache. On the other side, you can actually have direct mapping cache. Okay, what happened in that particular case is that the number of entry over here for one particular cache line is equal to 1. Okay, so when there's only one, when you have a miss, what you do is that you go and fetch the real page table entry, and when you bring that page table entry back, which one do you replace? Well, there's only one, so you don't have any choice. You just replace the one that you have. Okay, so one with the set associative cache with A-ways or something like that is that when you bring a cache line back, you need to decide which one to throw away. Okay, so if you need to decide which one to throw away, well, you need some sort of an algorithm in order for you to determine that. Okay, so that can get a little tricky. Okay, so the direct mapping cache, there's only one line, there's only one entry per line, so it's really easy to determine which one to replace. Okay, so these are the two extreme, and again, Intel, I think these days they use an A-way set associative cache in their translation look-aside buffer. All right, what about the situation where now you have multiple threads, okay, you have multiple processes, Okay, is it possible that you're going to have one thread that's running over here, and another thread that belongs to the same user process running in the other processor? Okay, then what we need to do is that we need to make sure that these translation look-aside buffer, when you try to, switch, user processes and stuff like that, you got to make sure that you flush out all the right caches. Okay, because what happens is that if this guy, okay, the code that's running over here, you're running in the operating system kernel, and you are changing the translation look-aside buffer for user process, okay? Then it is possible that the entry that you are modifying turns out to be used in another processor, right? Both of them can be running in the kernel, and you're modifying, a page table and stuff like that. Then one thread's execution might affect another thread's translation look-aside buffer. Okay, so what you need to do is that, it depends on what kind of hardware you have. Again, this is all in the hardware abstraction layer. You can have fancier hardware. You can actually invalidate one of the entry in the translation look-aside buffer, or you can invalidate the entire translation look-aside buffer. Okay, so typically all the processor, even the older one, they will support the operation to invalidate the entire translation look-aside buffer. To invalidate only one entry, that's kind of, fancier hardware can do that. Okay, so what we need to do is that we need to be able to invalidate translation look-aside buffer in the other processor. Okay, as it turns out, this is a little tricky, so you have to do it in the right way. Okay, so you have to actually run an algorithm in order to perform that. That algorithm is known as the shoot-down algorithm. Okay, so if you have, if you're trying to modify one of the mappings, and if you're trying to modify the mapping inside processor 1, you actually need to shoot down all the translation look-aside buffer in all the other processes, all the other processors. Okay, so what you need to do is that you need to go to all the other processor, find out whether they are running the same process or not. If they're running the same process, then you want to invalidate their translation look-aside buffer. If they're running a different process, well, then you know that whatever you modify is not going to affect them. Okay, so therefore you have to do this right. All right, you need to get the timing right. Okay, so what does that mean to get the timing right? Right, you want to make sure that the other processor are not actively using address translation. Right, because if they are actually doing address translation and you want to modify a page table entry, well, then that's really not good. Okay, so you want to make sure that all the other processor, they have to stop whatever they're doing. So basically it's like locking, right? So basically you want to lock some kind of a data structure, wait for all the other processor to, well, actually it sounds like the barrier synchronization, right? You want all the other processors to get to a place where it's safe for you to modify the page table entry. Okay, so what you need to do is that, here are the basic, code that's implementing hardware that's doing this. We're going to sort of see pseudocode. So this is the one that's shooting down all the other processor, and these are the code that has to be executed for all the other processor that are getting shut down. Okay, so the shooter code look like this. For all the processor I that are sharing the same address space using the same page table, what you need to do, you need to interrupt those processors. Okay, you need to pull their interrupt line to tell them to, so I guess there's going to be sort of translation look-aside buffer shoot down interrupt, okay, so that they can all go into the interrupt and wait for you to modify that page table entry. Okay, you want to interrupt all of them, okay, and then the shooter has to wait for all these processors to get to that nice place. Okay, so therefore it goes there for all the processors sharing the address space. You want all of them to acknowledge that they are in that nice place. Okay, so you check this global variable called node.i. Make sure that they all know that you are doing a shoot down. Okay, so you are initiating a shoot down. You want them all of them to say that I have noted that a shoot down is in progress. So therefore they will stop whatever they were doing. All right, and then what you do is that when all of them are in, when all of them are sort of synchronized with you, they all noted that you are in progress. Then you go ahead and modify your page table, because at that point, none of them are using that page table. Okay? If none of them are using that page table, what are they doing? They're servicing interrupts, right? I mean, that's the point, right? You interrupt all these things. Those processors might have interrupt disabled. Okay, so there you have to wait for them to enable interrupt. okay, and then they all are servicing all they are servicing the interrupt, okay. At that point, you know that none of them is going to access it in that user, page table, okay. So therefore, you can modify the page table, and then you can flush the translation look-aside buffer, okay, for all those processors. Oh, sorry, you're going to flush your own translation look-aside buffer, or if you have a fancier translation look-aside buffer, you can if you only want to update one entry, you can go ahead and do that, okay. And then you say that I'm done. Okay, so all the other processes, so all the other processors, they're executing this interrupt service routine, waiting for you to be done. All right, so how does that work? Okay, so here's the code for all the other processor, and this is the code for the translation look-aside buffer shoot down interrupt. Okay, so when they're starting to execute the interrupt code, they know that which processor they received the interrupt from. This way, they know which done to look for. Okay, so they're going to record that, they get an interrupt for processor J, all right? And then, this processor is processor I. It will say noted I is equal to 1, saying that I am now inside my TLB shoot down interrupt handler, and go ahead and modify the page table, okay? And then what it will do is they stay in the info loader over here, waiting for processor J to be done, okay? And when processor J is done, then this guy is going to continue execution. So, in this case, it can just simply flush its own translation look-aside buffer. All right, so please look at this code and make sure that you understand that this actually works, for synchronization with multiple processors. And then in the end, you're not going to have inconsistency problem with the page table entries. All right? Okay, so here is a sort of a page, a slide for storage cache hierarchy in today's system. Okay, so this one says that in today's system, some people call this a cache hierarchy, because you can think about what's inside your memory are actually cache of your disk. Okay, because when you're running a user process, right, the idea over here is that while you load up the data from the disk, right, the text segment, the data segment, because the basic idea is that you're sort of executing your code from the disk, okay, but this is too slow. That's why you have memory. You bring all those data from the disk into memory, so the memory is kind of like a cache for the disk. Okay, what about the disk? Is this also a cache? I mean, these days when you have cloud computing and stuff like that, well, then your local disk is kind of like a cache for your storage in the cloud. All right, so therefore you basically have a cache hierarchy, right? Your CPU is right here. Okay, here is your main memory, and here is your disk. Okay, and here is the internet. Right? Okay, and then this is the hierarchy. Okay, the general idea of a hierarchy is that the closer to the CPU, the cache hierarchy tends to be smaller, right? The cache device tends to be smaller, and it tends to be more expensive. Okay, the further away from the CPU, you can store a larger amount of data, but these devices are usually smaller. These devices are usually slower, right? So eventually, when you go to the cloud and try to fetch some data, well, that might take you a while. I mean, these days, I don't know, people are backing up, terabytes of information in the cloud. And if you try to look through the terabytes of information, it's going to take quite a while in order for you to find the data block that you need to copy into your local disk. Okay, so this is the cache hierarchy. In reality, these days the processor sort of look like this. Closest to the CPU is the translation look-aside buffer. The access time is about 1 nanosecond, and the size is quite small, about 64 kilobytes. Okay, and then there's some caches inside the CPU, L1 and L2, and I guess we didn't really talk about those, right? These are again hardware caches. And then comes the main memory. Okay, so over here it says that the main memory is actually 100 times slower than the translation look-aside buffer. Okay, so this is why you don't want to have 2 memory accesses to get into main memory. You only want 1 memory access. Okay, and main memory, right? Typically 10 gigabytes. I guess on our laptop we have 4 gigabytes, 8 gigabytes, etc. After that. These days, we have things like solid-state drive, SSDs. Okay, these things are 1,000 times slower than the RAM. Okay, the capacity is a little bigger. Okay, 10 times that. The next thing in the cache hierarchy over here is kind of weird. This says remote RAM. Okay, if you're on a data center has tons of computing power. They have lots of machines over there. One of the places to store data is actually it's on your neighbor's main memory. Okay, so you can actually get to your other machine on the local area network, get to their memory in about the same time as you access your SSD. Okay, so networking is actually very fast, right? Because you have gigabit Ethernet, or multiple gigabit Ethernet. So going across the network, interrupt the other processor to say, hey, give me some data. That's actually just as fast as going to the SSD. Okay, and in that case, you have pretty much the same storage because you don't want to use up too much storage on your neighbor's node. Okay, you have your neighbor's node. Part of them, if that neighbor will try to help you, then they will dedicate some part of their memory, for you. And then come the mechanical disk. The mechanical disk is the access time is about 1 to 10 milliseconds. Okay, but the storage is very big, right? It can go to 1 terabyte or several terabytes. And finally, remote disk in the local area network, you can combine all their disks, for one of your machines. So therefore, it's going to be, it's going to be 1,000 times, bigger. And then eventually you go to the internet, etc. Okay, so the cache hierarchy basically doesn't really have to stop. There's something called the Andrew file system, right? It was a file system that was designed by CMU. The idea is to put the file system of the entire planet under one, file system, so you can access any machine, through that file system. Okay, so the cache hierarchy can be actually very, very deep. As it turns out, there's actually something even before this. Okay, so when you go to a particular virtual address, right, you go through the address translation, okay, and you take it to a physical page number, you add that physical page number, shift to 12 bits, add to the offset, you get that data. Okay, what if you want to access that data a lot? Okay, so when you finish reading that data, you can actually cache it inside your CPU. Okay, so actually right before the TLB over here, there could be another cache. Okay, the speed is going to be, pretty much just as fast as the translation local-site buffer. And that one, I guess there's some people call it the virtually addressed cache. Okay, so anyways, this is not the end. There actually can be multiple levels of additional caches that are here, that are there. There are also things like instruction cache that just cache the instruction that are inside the CPU. All right, anyways, TLB, so anything above this line, okay, these things are managed inside hardware. Okay, and the only thing that OS can do is to invalidate entries in them. All right, and the CPU will have a special instruction for you to invalidate, these caches. Okay. Finally, I just want to briefly mention about the 64-bit issue. So we've been assuming that the address space, the virtual address is 32-bit long. What if you have a 64-bit processor, right? The address is 64 bits long. All right, so we actually use this scheme, all right, multi-level, right, 1, 2, 3, 4, 5, 6 level. So as it turns out that this one is actually done in the Intel clone, the AMD processor, they use this particular scheme. Okay, and it turns out that this one is so popular that the Intel scheme is actually not being used. Okay, so by default, everybody's using the AMD scheme. Okay, and do you really need 64-bit address? I mean, the address space is way too large, right? There's really, it doesn't really make sense. So actually, in the first 16 bits over here are unused in the AMD scheme. Okay, so this is called the AMD. This is called the x86-64 format. Okay, so that's why when you download your Ubuntu Linux, right, it says AMD 64. Okay, it doesn't say IA64. Intel uses IA64, right? But typically we use AMD 64. Okay, so we're going to assume that the address translation for the processor is in this format. Okay, the i386 is the one with the 32-bit format. There are two formats. One is like this, and the other one is combine the last two fields into one field. So instead of having 5 fields, you only have 4 fields over here. Okay, and again, the translation local-site performance is going to be very, very crucial for this particular architecture to be successful. Right, because if translation local-site buffer is 100 times faster than main memory, then if you go to main memory for every one of these page table, then it's going to be 4 nanoseconds, sort of 4 microseconds, instead of only 1 microsecond. Okay, that would be way too slow. All right, Intel uses this, I guess I have a gray X over here. So Intel used IA64, okay, IA64, the last people who used it was, I guess, was the HP Itanium series of machines. And I guess a couple of years ago, HP says, we give up, we don't want to deal with this format. So this one, this architecture, I guess nobody's using this, okay? You probably heard of IA64, okay? So the basic, structure is using something that looks like a linear page table, right? A linear page table has a space over here, followed by, the page number, and then followed by address, by the offset, okay? So this particular scheme turns out to be very, very similar to the linear page table, and they do the similar kind of translation that on the slide that I skipped, for the VAX machine. Anyway, it's no longer popular, so we're going to skip. Actually, it's no longer supported. I guess nobody's using it. All right, so the next part, I'm also going to skip it, and this is on virtualization. Since we haven't really talked about virtual machines, we're going to virtual machines covering Chapter 4. After we finish Chapter 7, we're going to go back to Chapter 6, and then go back to Chapter 4, and then eventually when we finish Chapter 4, we're going to come back and look at virtual memory support for virtual machines. All right, so now what we need to go is Chapter 7.3, and look at the operating system issues to support virtual memory. All right, so, the hardware stuff that we look at, this you need to understand, okay, especially paying attention, as far as your kernel assignment is concerned, you need to only pay attention to the multi-level, page directory, page entry, because, we're doing stuff on Intel, so therefore that's the kind of architecture that you should be focusing on. All right, all the other stuff are, I guess you're responsible for your exams, but for the kernel 3, only the Intel format. All right, so in operating system, these are the sort of the general issue that we need to concern, okay? When we use virtual memory, we have to worry about things like fetch policy, replacement policy, placement policy. We're going to see what these things mean. Okay, so the fetch policy, so the basic idea of fetch policy is that we're going to use the validity bit inside the page table entry. And in the beginning, when we start a user process, okay, we start off a user process. Okay, so let's say that this is the page table. Okay, and again, I'm going to talk about page table at the high level. Forget about multi-level or something like that. Using the basic approach, only a single page table, and this page table has 1 million entry. Okay, and every entry take up 4 bytes. Okay, and inside every byte there is validity, modified, reference, protection, and then finally the physical page number. All right. So inside the page table, what we're going to do in the beginning is that, the fetch policy is we're going to set v equal to 0 for every entry over here. Okay, so when we start off a user process, okay, the user process, we're going to say, well, what page does it, does it point to? Well, it points to nothing. Everything is invalid. Okay, so as soon as the user process is trying to do anything, it will page fault into the kernel, and the kernel is going to fix everything. And the kernel is going to fix only one entry at a time. Okay, so which entry should the kernel fix? The kernel should only fix the entry that the user process really need to, the user process really need right then. Okay, so when the user process try to access one memory location, you will fix the page table entry for that memory location. Okay, and then the user process is going to generate another memory reference. If that one is invalid, then you go ahead and fix it. Okay, so again, if you in the beginning you start executing your code, the first thing that your user process is going to do, right, after you do exec-L, okay, is going to start executing the startup routine right before the main program, right? We call it, startup or something like that. So that one is going to generate the first memory reference to the text segment. Okay, so at that point, we're going to page fault into the kernel, and the kernel is going to find a place for that particular page, and then fix the page table entry, and then restart that memory reference. And the second time when when that memory reference is used, then you better get a hit, and then you will be able to use that entry. Okay, and then from that point on, the next few instructions, you're supposed to, be accessing the same page with the validity equal to 1. But then after you run for a while, then you're going to access another page where the validity is going to be equal to 0. You page fault into the kernel is going to set it to 1, etc. Okay, so this particular style is called on-demand paging. Okay, so we're going to sort of do paging on demand, and that's going to be our fetch policy, right? So the idea over here is that when we try to fetch a page from disk and move it into memory, what is our fetch policy? Well, we should do fetching on demand. Okay, only if the user process needs it, then we go get it. If the user process doesn't say, it needs it, then we're going to leave it on the disk. Okay, so in a way, I mean, this is sort of a scheme that's known as lazy evaluation. Okay, lazy evaluation says that, if you want to evaluate something, so for example, I have an expression S is equal to, phi plus Z plus K plus whatever, right? Okay, so when do I evaluate this expression? Okay, I want to evaluate this expression as late as possible. Okay, if I don't need to, if I don't really need X, why do I have to evaluate this expression? Okay, I want to delay my evaluation until the last possible moment. Okay, the last possible moment is that when I need the value of X. Okay, so you will actually store X as an expression and store that, sort of as an expression that says what X has, what X needs to be. Okay, but don't really evaluate X. Okay, evaluate this as late as possible. Right, so we're doing the same thing over here. Okay, that when we want a page, when we want a particular page to be in memory, this page might be sitting on disk at the current time. We don't bring it in until we absolutely have to have it. Okay, so why do we do this? Well, maybe because we might not have to even bring that page in. Okay, so if you think about your warm-up 1 and 2, right? Okay, and you try to do, your login shell, you do a fork and you do an exec-L, warm-up 1 or warm-up 2. Are there cases you don't need most of the memory pages that are on disk? Okay, remember, right, on disk, the executable has text segment, has data segment, has BSS, all that kind of stuff, right? I'm claiming that, sometimes you don't really need all that thing in memory. Sometimes you can leave them on the disk. Okay, I mean, clearly, if the command line argument is incorrect, okay, then most of your code is not going to execute, right? You're only going to execute the part where it says, you print an error saying malform command and you call exit. Okay, so therefore it is possible that you have a user process that, a lot of the code that are sitting on disk, you never really need to bring into memory. Okay, think about if you are the program Microsoft Word. Okay, Microsoft Word is a very, very large program. Okay, if you fire up Microsoft Word, how much of the text segment do you really use? Okay, maybe a small portion of the text segment, right? Because you're not going to use most of the plugin. The plugins are a lot of code, on disk. Okay, so therefore it's actually reasonable to do this on demand. You only bring stuff that you actually need. All the other stuff, if you don't bring them in, then you don't need to commit physical memory to store those data. Okay, so in the end, it is the physical memory that are precious. Okay, if you load up all your physical memory with data that you don't really need, then eventually you have to throw them out and bring something that you need and to replace that page of physical memory. All right, so therefore the philosophy of lazy evaluation actually apply really, really well in the fetch policy of the operating system when it comes to virtual memory. Okay? All right, so the lazy evaluation actually, so this is sort of a general principle. If you have have you heard of like stream processing or something like that? That people are processing streams, data stream coming from a remote place. In order for you to process that particular stream, how do you really process that stream? Okay, the stream may be satellite data coming at a really, really high speed, and you don't really want to process the entire stream. Okay, so what you can do is that you want to delay process that data as late as possible. Only when somebody needs that data, that's when you process it. Okay, so you will stream those data onto disk, and maybe you will tag them with some information about timestamp and stuff like that. So later on, when you need to go to that piece of data, you want to process that data only at the time when somebody needs that data. All right, I mean that might be a little too simplistic, but the idea over here is that if you can generate some kind of a description of that particular data, maybe you can actually save some CPU time, so you don't waste processing data that you don't need. All right. Okay. Anyways, that's not completely stream processing. I'm just using that as an example. All right, so that's fetch policy. What about placement policy? Okay, when you put data in memory, doesn't matter where you put that piece of data. Okay, when we try to fetch stuff, since we're doing paging, we're fetching 4 kilobytes pages at a time, right? Okay, and we divide both physical memory and virtual memory into 4 kilobyte pages. So as it turns out that because of the nature of physical memory, it doesn't really matter where you place them. The access time of these pages are exactly the same. If you put them at the beginning of the physical memory, or put it at the end of the physical memory, put it in the middle of the physical memory, the access time is all the same. Okay, so therefore the placement policy is that it doesn't really matter. You can put it anywhere. Okay, so this is unlike disk. When you put stuff on the disk, you actually have to worry about where you put them. Right? Remember the improvement that we saw going from the system file system to the file system. One of the things that we did was that we put we put files that are referenced together. We put them right next to each other on the disk. Okay, so this way, when you go to one directory and you want to look for a file that in that directory, all you have to do is to have local searches. Okay, and that's much, much faster. Okay, for a disk, if you put those files at a different place, then you have to perform a full seek to find those files, and that's going to be really, really slow. Okay, memory is not a device like that. If you want to go to another place in memory, it takes exactly the same time as if you are referencing the next page. Okay, so therefore, placement file policy for virtual memory is very straightforward. What about replacement policy? Right, replacement policy meaning that, well, all your physical memory are being used. Now you try to bring a new page, right, because some user, try to access some code, and that page of data is sitting on disk. You want to bring it into memory, okay? Since your physical memory is completely full, you have to throw something out in order to make space to bring the new page. Okay, so that's replacement policy. Which page do you replace so to create a hole to put in the new memory? Okay, so this is basically a resource management problem. Okay, so once you decide that the fetch policy is on demand, so there's really nothing much to it. You set v is equal to 0 for every page and bring it in as you need it. Placement policy is very, very straightforward. So it turns out that the replacement policy is where some of the complexity comes in. All right, so this is a little bit tricky to decide which one. And I sort of mentioned, right, like in the translation local site buffer, if you have a miss and you try to bring something, and if you have a set associative translation local site buffer, you need to decide which one to throw out. Well, that's the same kind of problem. All right? Okay, so those are the things that we're going to look at, in this in the beginning part of this slide. All right, so we're going to sort of briefly walk through this example for on-demand paging. Right, we're going back to on-demand again. Okay, so the basic idea is that when you run execl, okay, you replace the address space of the user process with a brand new one. Okay, in that case, we're going to reset the page table to 0. Okay, so how do you do that? Memset, right? Okay, so you do memset, the beginning of the page table, and one shot, and they all become 0, so all the validity bits become clear. We don't care about all the other bits, right? Because as long as v is equal to 0, the other bit can be garbage, and we don't care. So we can actually, instead of going through every entry, set it to 0, we do a memset, and the whole page table is going to get cleared. All right, so this is really easy, right? Okay, and then what we do is that, okay, so now we have a new user process, okay, and you're starting to do execl, right? So the first thing that happened is that you're going to fetch an instruction. All right, so how does the user process start executing? Right, so again, right, you do execl, okay, execl, you go in, it's a trap, it's a system call. You trap into the operating system. Okay, the operating system basically now have to, return to the child process. Or you start with 2 processes. One process, you fork a child process. The child you do execl, wipe out the entire address space, right? And the way that you go back to the user process again, it's return from interrupt, right? That's the only way that you can execute. That you can go from the user space to kernel is to execute return from interrupt. Okay, so what you need to do is that when you implement your execl, when you wipe out the address space, you have to set things up so that you make it as if the user process make a system call, and then you're going to return to whatever it was doing before. Okay? Except that in this case, whatever you're doing before is something that it was never done in this user process because you just wipe out the entire address space. All right? So inside the kernel, you need to prepare the address space, make everything look right. You got to prepare a brand new page table, clear out all the entries, and now you return to user process by using the interrupt return. But now you're going to set up all the data structures so that when you return, you're going to execute the first instruction, of the user process for the first time. All right? So basically, the next thing that you're going to do in the user process is that the EIP register is going to be set to point to the text segment over here, and you're going to execute a fetch of a machine instruction so that you can execute that instruction in the CPU. All right? So this is what the startup routine does. Right? Startup routine gives you a beginning place to execute the first instruction of the user process. And what do you do there? Right? I mean, you call main, right? Okay, you call main, and then you wait for main to return, and then whatever return code the main returns, and the return code is set in the EAX register, right? Okay, and then you use that to call exit. All right, so that's what the startup routine does. Okay, so therefore in that case, what you do is that you will access this memory location. Okay, this memory location, you're going to get a virtual address. It's going to be a low memory address, right? So you're going to point to this location. And this location has the validity bit set equal to 0. Okay, so therefore the address translation is going to generate a page file you trap into the operating system. Okay, the operating system is going to say, oh, this is the the current process that's running. Okay, and this is the virtual memory address it's trying to generate. What do I need to do? Okay, so now the operating system needs to walk down the address space data structure and decide what needs to be done to see if this is a good memory reference or it's a bad memory reference. Okay? If you're referencing memory location 0, that's a bad memory reference. But if you're referencing the text segment for this user process, well, that's perfectly good. Now the operating system needs to go to the disk and fetch that page and put it in memory and then adjust the page table. All right. So, since v equal to 0, how we're trapped into the kernel allocates a physical page. Okay, so again, the physical memory, right, there are many, many pages. If you have, 1 gigabyte of memory, right, you have, 2 to the 18 pages. Okay, so you go to the 2 to the 18 pages, you find a free page. So how do you find a free page? Right, you go to the memory allocator. So again, that's where memory allocation come in, right? Okay, so the kernel memory allocator does not use the first fit memory allocation, does not use the first fit memory allocator. The kernel memory allocator usually use the buddy system. All right, so in that case, in order for the kernel to find this page, it will query the buddy system to say, hey, give me a new page. Okay, give me a page that's not being used. All right, so the buddy system maintains the data structure for the pages that are free and for the pages that are in use. It will go to the free page list. You have to split the data structure if it has to, and eventually it will give you a 4 kilobyte page. All right, so you do page allocation, and that's how you get one of these pages. All right, so this page is where the data is supposed to go to, right? And then you initiate a disk operation to transfer data into this page. All right, so the disk will transfer data into this page, right? And during that time, you probably want to lock down this page so that they don't accidentally get swapped out. Okay. And then eventually when this guy is filled with data, then the disk is going to generate interrupt. Okay, in the interrupt service routine, what do? Right, you start off another disk operation and you unblock a thread. All right, so which thread do you unblock? Right, so this is the kernel thread that's fixing this page fault, is handling this page fault on behalf of this user process. So that's the kernel thread that you're unblocking. When this kernel thread unblocks, it will continue doing whatever it's supposed to be doing. In that case, what it will include is to update the kernel data structure and then set the page table entry for this guy so that validity is equal to 1. And then it's going to do interrupt return to return to the user process so the user process can repeat that memory reference. Okay? So now, after all that, right, so all this is to fetch the instruction for the first memory reference, okay, for the user process. Okay, and then it will repeat, and the second time when it repeats, then, validity bit equal to 1, and hopefully the page table entry, what you said, is correct. Okay, if it's correct, what's going to happen is that this time it's going to be cached into the translation local site buffer inside the CPU, and also it's going to be able to fetch that data from main memory. Okay, and at this time, this physical page number better point to this page so that the data, so you do the left shift 12 bits, add the offset, and get this memory location, and that's going to be the first instruction that you need to execute. All right, in order for you to see, again, this is sort of kernel 3 stuff, in order for you to see one instruction that will be the first instruction you will execute, you need to run the program object dump, okay, and dump the executable so you know what the first instruction has to be. All right, so I'm going to jump to the, the kernel 3 a little bit, right? In kernel 3, that's sort of one of the things that you have to debug, okay? Whenever you start off the first user process, this is what needs to happen, okay? So what you need to do is to debug this process, make sure every bit everywhere is set just right, so that when the user process is restarted, to restart that memory reference, it's going to go through the page table, and this page table better point to the page that just got allocated, and the offset is going to have that first instruction that you see in the object dump, have that machine instruction right there. Okay, the bit pattern better match, otherwise you're going to fetch some garbage in there, and you're going to create another illegal instruction, fault or something like that. Or if your page table is not pointing to the right place, or the bits are not set correctly, you're going to get another page fault, and you go back into the kernel. All right, so sort of a preview of what you have to do. All right, so this continues, right? So you're going to execute a few instructions over here. Okay, this picture shows that your program may access, global data, right? So you will make a reference to the data segment. The data segment over here in the picture, it shows that it points to this page. Validity bit equal to 0. You go through exactly the same thing. Okay? You fetch that page. While you're typing the operating system, you fetch that page. You find a page. You lock it down. You initiate a disk transfer. Wait for the disk interrupt, unblock the kernel thread, and then set the validity bit back into 1, and then return back to user space. Okay? When the user's process is going to access the stack, does it access the stack right away? Right? I mean, remember that the user, the user process in the startup routine, the first thing it does is that it's going to call main, right? Main has 2 arguments, argv and argc. Yeah, so you need to access the stack pretty soon. Okay, so the same thing happened for the stack, right? Points to something, it needs to be set to 1, etc. Okay, so this is basically how demand paging works. Okay, and keep in mind that every user process has their own separate page table. So when you switch to a different user process, right? Here's one user process, here's another user process. You got to make sure that the correct page table is being used. And on Intel, what you need to do is to set the CR3 register to point to the right page table. Okay, and while Intel is the page directory table, but conceptually you're pointing to the page table. All right, so this sort of summarizes the steps. Okay, I guess this is kind of repetitive because this process is very, very important. You need to really understand the step, perfectly clear so that you can implement it just right. Okay? I mean, the top part inside the kernel assignment is that, where do you find all this information? How do you walk down the kernel data structure? How do you repair the kernel data structure, so that they get into the right state? Okay? You want to make sure that when you return back into the user process, everything needs to be perfect, right? Because anything that's wrong, you're going to cause problem in the future. Okay? All right, the trap occurs, you find a free physical page, okay? If you cannot find a free physical page, that means that all the physical pages are being used, okay? Then you need to do your replacement policy and then decide you want to take one page and then send it out to the disk, okay? So in that case, if that page is not dirty, right, remember the page table entry has a dirty bit in it, right? Okay, if that page table entry is not dirty, then you can just free that page. Okay? If that page is dirty, that means that the physical content of that page does not match what's on the disk. So therefore, you have to write that page out first to the disk before you can discard that page. Okay, so therefore, that's step number 3 over here. You need to write the page out, if there's no free physical page, okay, and also if that page is dirty. Okay, and then you have to wait for that operation is done, right? Because at this point, there's no free physical pages. So in order for you to continue this thread that caused the page fall, well, you have no choice but to wait for this operation to finish. Okay, when it finished writing that page out to disk, then that page becomes the free page that you can use in step 2 over here. Okay, and then you do the second disk operation. You fetch the page from the disk into that page, and then when the disk operation is finished, you set everything back up, and then you return from trap. All right, so these are the things that you have to go through. All right, again, here's an example. I have 10 pages in physical memory, right? Over here, I said PF0 to PF9, right? So these are the page frame. And again, page frame, there's a one-to-one correspondence between page frame and physical page. So you can think of them as, physical pages. Okay? So the first user process, and of course over here, the operating system is not using any pages, so that's wrong. So some of them are hidden. So this picture is just for illustration purposes. The first application has 1, 2, 3 pages that are active, and they're pointing to this one, and this one. Okay, so this belongs to process 1. Process number 2 has 1, 2, 3, 4 active, so this belongs to 2. This one belongs to 2. This one belongs to 2, and then this one belongs to 2. And the third one has 3 pages that are active, 3, 3, and 3. Okay, so all the pages are used. Okay, and now if you come with the fourth user process, okay, in the beginning everything is 0, right? So now if you try to execute this user process, so by the way, where did the fourth user process come from? The fourth user process comes from a fork, right? So when you first fork from one of the applications, in that case, in the beginning, the page table entry for that user process, how do you construct that page table? Right? If this is the parent process that fork off application number 4, right? You do a mem copy, right? You take this entire page table, just copy over here, and then you can share all the pages. Okay? The data pages, when you share, you got to be a little careful. But the idea over here is that you can do a mem copy to copy this page table. All right? But as soon as you do exec L, you have to wipe out the entire thing, construct a new page table, do a mem set everything equal to 0, and now you have to go through, and then you start executing the first instruction. Right? The first instruction is going to cause a page fall, and then you have to go through that 5 steps. All right, so in that case, what you would need to do is that you trap into the operating system because of validity bit equal to 0, okay? You don't have a free page frame, right? So you need to find a free page frame to swap out, right? So over here, I use the term swap out because this one, you swap it out to the disk because later on, you'll be able to swap it back in. All right, so you're going to look up the kernel data structure to find the backing store for this particular page frame, okay? In this case, you find, in this example, page frame number 5 has a backing store this place sitting on the disk. All right, so therefore, you will check the dirty bit to see if this page is dirty. If it's dirty, you have to write out the disk. If it's not dirty, you can just free up this page. All right, so this example, the page is dirty, we'll write to the disk. Okay, and then this page becomes free, right? So this is going to be the one that we free up, right? Once this data becomes the same as the disk, then this page becomes free. Okay, if this page is not dirty, which means that the page content is the same as the backing store, then therefore you can use it right away, right? Either case. All right, so in this case, this page is now free, right? So therefore, what you do is that you go to the kernel data structure that correspond to application number 4. What kernel data structure, right? Well, you just execute exec L. You go to the disk and you parse the content of the executable file. You find out how big is the data segment is, how big the text segment is. You know exactly what you need to do to build up the kernel data structure to support this application. All right. So at that point, this is the first instruction, so it points to a place on disk, right? So this is going to be the page on disk. You're going to read this page into the page frame that you just freed up, Okay, and once you finish loading this page into the page frame in the disk the disk interrupt routine, you unblock the kernel thread so that this kernel thread continues to execute, and then set this bit to 1, and then you can return back to the user process. And when you're back to the user process is going to restart the operation, and this time it's going to get a hit, and then it will continue to execute. All right, again, it's going to execute a few instructions, getting hit on this page, for a few instructions before it needs another page again. All right? Okay, so over here, we sort of talk about that this process is very, very slow. If you need to look for a page, in the physical memory, right? If we go back to the previous page. Okay, so over here, you got to look for a page. If all the page frames are being used, you need to look for one that's free. Okay, and then you have to write this thing, you got to write this page to disk, and that's really waiting too long, right? So this means that in order for you to fix the first page fault, you actually have to access the disk twice. Okay, writing one page out to disk, and then read a page back, right? Of course, not all these pages are dirty. Some of the pages are dirty, some of the pages are not. You can say, well, I'm going to look for one that's not dirty, and then swap them out. Okay, so again, if you do that, well, it's going to take you a longer time to just look for it. Okay, the number of pages over here can be very, very large, right? If you have 1 gigabyte of memory, there's a quarter of a quarter of a million pages that you have to look through. Okay, so this performance is really not acceptable. Okay, so you want to be able to find, to find a free page very quickly. So if you use the buddy system, and if you have a free page, well, that can be done really quickly. Okay, but in order for you to search through the pages to find something to replace, well, that's going to take a while. Okay, the buddy system is good for finding free pages, but they are not very good for finding pages that are busy. Okay, so therefore we really need to speed up this process, and also writing to disk is slow. Okay, so we really want to get rid of all this time that you spend waiting for to look through the buddy system and also to write out the page. All right, so that's about the replacement policy. Okay, so to reduce this latency, one way to do it doesn't really help that much is to do prefetching. Okay, if you are accessing the disk, right? If you go to the text segment, okay, and the text segment, let's say there are 8 pages over here. Okay, when you fetch the first page in the text segment, why don't I bring in the other 8 pages? Because I know that I'm going to start executing my code. Sooner or later, I'm going to need those pages. Okay, so this is called prefetching. So what you do is that at the time you fetch the first page, okay, you're going to free up 8 pages, and you're going to load those 8 pages, from disk, okay, so that, the next 8 pages, the next 7 pages that you're going to access, you don't have to wait too long. Okay, but in this case, again, it doesn't really help because you need to search through the data structure. That might be too slow. Okay, so another approach is to use something called the page out daemon. Okay, so the page out daemon, basically what it says is that when you look at this data structure, okay, I'm going to do the opposite of lazy evaluation, right? Lazy evaluation says I want to do things as late as possible, and the opposite of that will be doing things as early as possible. Okay, so the idea over here is I'm going to go through all these pages. I'm going to start swapping them out to disk, all of them. I'm going to be very, very aggressive, right? So lazy, the opposite of lazy is aggressive. Okay, I'm going to be very, very aggressive. I'm going to start swapping all these pages out to disk. Okay, because this guy is going to execute, so it has higher priority. I'm going to swap all of them out to disk. Of course, that's too aggressive. Okay, so you don't want to swap them all out to disk. You only want to swap some of them out to disk. Which one do you want to swap out to disk? All right, so these pages, they belong to all different kinds of user processes. Okay, and now the operating system is in charge over here, and the page out daemon is running as a separate user process using a separate kernel thread. Okay, so what we're going to do is that we're going to have the page out daemon. Basically, it will scan all the pages, go to the buddy system, scan through all the pages to see which one is not needed. Okay, so how do you determine which one is not needed? All right, so that determines the replacement policy, right? The replacement policy is saying that which one do you want to throw out, okay? And what do we do? So one thing that you can do, you can put everything in the linked list, okay? And we're going to use the first in, first out policy. So basically, all the pages, all the page frames, we're going to put it in the linked list. We're going to sort them according to the timestamp that these pages was brought in to the operating system, okay? And we're going to say, well, the page that was brought in first is going to be the first one that we're going to swap out. All right, is that a good policy? No, right? Because in the beginning you swap, you use a lot of kernel pages, then you're going to use them for your kernel. So you don't really want to, just swap pages out just because they came in first. Okay. I mean, the problem for determine, what page to throw out is that you have to look at the timestamp of these pages. So when can you have a timestamp for a page? Okay, I mean, if I have all these pages, these page frames, right? Page frame, every one of them has a timestamp. Okay, when do I stamp them? Okay, I mean, the only time you can stamp them is when they're in the kernel, right? Okay, normally your processor is busy serving, running user processes. They're really not doing the kernel stuff. Okay, so you can put a timestamp in when the kernel is in charge. And when is the kernel in charge? Well, when you get a page fault and stuff like that. Okay, so when I allocate a new page inside the kernel, at that time I know exactly what time it is, so I can actually put a timestamp on it. All right, but the first in, first out is really not a good way to go. Okay, so we've got to use some other policy. What about last in, first out? Right, last in, first out is like a stack data structure, right? If you have a stack data structure, right, you push stuff on the top, and then you pop up all the stack, right? That's a last in, first out data structure. Is that a good policy? Right, that means that the one that you just allocated, that you just created,
the time is
you just
13
allocated,
o'clock.
that's the one you're going to remove first. Okay, so that's clearly a really bad policy. Okay, those of you who have taken CS570, right, know there's another policy called the most recently used policy. Okay, so if maybe I should go back to that page. Okay, if you sort them based on the recently, 1 minute, the most recently used timestamp, right? Like this will be the least recently used, and this is the most recently used. Okay, so this one is the one that I used most recently. Okay, then I will, look at a page and say, well, this one I haven't used for a very, very long time. So then I'm gonna, that's the one I'm gonna replace. Okay, but how do you know this one is least recently used? The only time that you have to shuffle this list is when you're inside the kernel. Okay, so therefore, it turns out it's a little tricky to find out, to implement the least recently used. If you take a 570, you actually see a proof to show that least recently used, under certain condition, is the optimal policy. All right, so if you want to replace anything, least recently used is a good way to go. But how do you implement that, in the operating system? That turns out to be tricky. All right, so next time we're going to cover that. We're going to finish chapter 7. All right.
I'm confused with the vput and reference thing.
You mean the reference counting stuff?
Yes, sir.
Yeah, it's hard to get it right.
Actually, there are functions like.
That concludes CS 402 on Monday, July 14th, 2014.